Hey everybody, this is Miss Quinones. We're going to start working on our guided notes right now. And I just want to remind you that once you're done, you're going to come back into Google Classroom and find this classwork assignment that has some extra theoretical probability practice. You may not see it if you look in Google Classroom right now, but it is scheduled to post by the time you're done with your notes for today. Let's make sure we put our first and last names on here as well because we are going to be turning these in to the drawer at the end of the period. So today we're going to really analyze the difference between theoretical and experimental probability. So we're going to start with our definitions. So theoretical probability means what should happen in an experiment. Okay, those are my quotes right there. And if at any time you feel like you need a little more time, remember you can always pause. Okay. So this is what math tells us should happen in an experiment. Okay. So we were looking at a coin toss. A coin toss has 50-50, right? 1/2 probability to it. So if I toss it 100 times, I can expect to land on heads approximately 50 times. Experimental probability, this is what we've already been talking about also with relative frequency. The difference is it shows what actually happens in an experiment. So we're looking at basically theory versus actuality. Okay. And so today we're going to analyze some of those results using a popular game of rock, paper, scissors. Okay, so again, you can pause if you need more time. So we're going to start by looking at the theoretical probability of rock, paper, scissors. Okay, so we're going to fill in our chart, complete it, showing who would win the game under these different combinations. Okay, so if I have player A doing rock and player B doing rock, we call that a draw. So then we go ahead and we put the dash through it. If player A has paper and player B has rock, that means that player A would be the winner because paper covers rock. If player A selects scissors, player B selects rock, then that means that player B is the winner. So let's go ahead and have you pause the video right now, and let's have you fill in the rest of the chart by yourself, okay, and decide who the winners are going to be. All right. Hopefully you paused. All right, I'm going to save some time over here by having them filled in now. And what you're going to notice is that this is showing the 9 different combinations that can occur when you're playing rock, paper, scissors. Okay, so if I'm looking for player A to win, then I notice that there's 3 A's here out of 9 possible A's. And of course, we've learned to reduce our fractions. And if I write that down as a percentage, I'm going to get about 33.3%, okay, with that line over it. You'll notice player B winning is going to be the same exact data, right? 3 times out of 9, reducing to 1/3 and 33.3, repeating decimal percentage. And this is really why we do rock, paper, scissors so many times, because it's considered a fair game, because it's equally likely. If we're looking at a tie, surprise, surprise, same data. Okay. Now, if we would have been in class together today, then I would have actually had us do this activity together where we do the actual experimental probability. But since we're not, I'm just going to use data from a previous class that's conducted the experiment. Okay. So in this class, we did 25 trials of rock, paper, scissors, and these are going to be the results that we got in those 25 rounds. Okay. Player A won 9 times, player B won 7 times, and there was a tie 9 different times. So we're going to now take this data and we're going to compare it to the theory of what math told us should happen. So for this first percentage, I'm going to write my fraction as 9 out of 25. If I use my calculator to convert that to a percentage, I get a decimal of 0.36, which converts to approximately 36%, so a little bit higher than the theory. When I look at player B winning, player B only won 7 times. So this time it's going to say 7 out of 25 total trials. And when I divide that out on my calculator, I get 0.28, which is approximately 28%. All right, feel free to pause and to check things on your calculator as well. Okay, my final one is tie, and tie was actually tied with player A, so it's the same data. 9 out of 25, 0.36 or 36%. So when we look at these numbers, I want you to notice that they're not the same, and they don't have to be the same, because what our definition told us is that experimental probability is what actually happened, and it doesn't have to match the theoretical probability. So for this question over here, do the theoretical results match? They don't match. And the reason they don't match is because we actually didn't do enough trials to really make it mathematically accurate for our experiment. And of course, an experiment always involves some luck. So how could I have these results get closer to what math tells us should happen? Well, what I would do is I would conduct more trials. Okay, so this is a big idea in probability, is the more trials you do, the more times you conduct an experiment, it's going to get us closer to accuracy. So more trials will be more accurate. Okay. And again, if I'm writing too fast, feel free to pause and take your time writing it down. Okay. The next thing we're going to do is we're going to take these two ideas and then we're going to be doing some practice with them by doing some examples together. Okay, so we really want to pay attention to the words because this is going to be coming up in our homework next week. So over here we have a table and we're rolling a standard die. If you recall, a standard die has 6 sides to it. Okay, so my first question is asking about the theoretical probability of rolling a 4. Well, a standard die would only have 1 4 out of 6 different sides, right? And we're going to actually just leave this as a fraction because our directions aren't asking us to convert it to anything else. And I can't reduce my fraction anymore, so we're good to go. My second question, instead of saying theoretical, it's asking about the experimental probability, okay, of rolling a 4. So now, instead of looking at math, I'm going to look at what actually happened. So when we look at the data here, the 4 was actually rolled 5 times out of 50 total possible. So for my fraction, I'm going to write 5 out of 50. And of course, reduce to lowest terms when possible is 1/10. So I want you to notice over here when you compare the two, let me circle this one too so they look the same, that the results show that this second one is actually lower than what I would expect the math to tell me that it was in the theoretical probability. And that's okay, they don't always have to be the same, right? For question 10, we've got a spinner, okay, and we're going to start with the theoretical probability. So again, for the theoretical probability, we're looking at what math tells us should happen. So I'm going to analyze the spinner instead of analyzing the chart, okay? So on my spinner, I see that there are 8 different sections. So that's going to be my denominator. And the question is asking about a shaded letter. So when I look, I see 3 plus 3 makes 6 shaded letters. When I reduce to lowest terms, I get 3/4. So that's my theoretical probability of spinning a shaded letter. Now for the experimental probability, this is where I look at the actual chart, right? Because that's what actually happened. So when I look at my chart over here, here's my data for A, B, and C. And A, B, and C were my first 3 shaded. Then I have E, F, and G. Those are my next shaded. So in order to find my numerator, I'm going to have to add these up, the frequencies, okay? So when I add all these frequencies up, I got the number 60. In order to write my denominator, I'm going to go back and look over here and say, all right, the trial was conducted 75 times. So that makes it my denominator. Of course, reducing to lowest terms, when I reduce these both by the number 15, I end up getting 4 out of 5. Again, my results are not the same, and they don't need to be the same. This time, the experiment was actually higher than what math would tell me to expect it to be. Okay, so that's how we compare theoretical with experimental. Now we're going to do some proportion practice like we did yesterday when we were doing our application question, all right? So here we have a table that shows the results of tossing a coin 100 times, so that of course is important. First, it's asking theoretically, so let's make sure we pay attention to that. Theoretically means not based on the data, but based on the actual math. So if we're looking at a fair coin, the theoretical probability is that you're going to get heads 1 out of 2 times, right? 2 possible times. To build my proportion, I'm going to have my equal sign. Now, the expectation is asking about 300 tosses. So just like yesterday's proportion, we're going to need to set it up and put that 300 in our denominator. All right, so one of the strategies we did yesterday was using scale factor to solve, but today we're going to practice some cross products instead. So we're going to multiply 2 times x, and we're going to multiply 300 times 1, and proportions always have equal cross products. Now we use our equation solving skills over here to isolate our variable, and I can expect to land 150 out of 300 times. Okay, now based on the experiment, if I do this same exact question, I may not get the same answer because now I'm looking at the data. Well, on the data, I landed on heads 58 times out of 100. I'm still going to look at my expectation for 300. So by yourself this time, can you pause it? And let's have you solve this one, okay? All right, so when you solve this, hopefully you paused it and tried solving it and you did your cross products over here. You should have ended up with a statement that looked like this, okay? And we can always do scale factor, but I wanted you to practice your cross product skills today. Using our equation solving skills from previous modules, my expectation or my sample is going to predict 174 times. All right, so now on your own, let's get you to try question number 12, both parts of it. All right, so let's have you pause it and let's have you try it by yourself. All right, so hopefully you tried it by yourself, and this time I'm going to use my already done sample because I'm running out of time on my video over here, okay? So in theory, if I'm looking at my letters selected randomly 500 times, when I look over here, I had 2 vowels in my chart out of 7 total letters. So my first ratio was 2/7, and then I set up my proportion. From here, I set up my equation, solve to isolate my variable, and I'm getting approximately 143 times. Even with scale factor, you should get the same answer. When I based it on the experiment, I actually added my data together. So that's where we did 6 plus 18 gave me 24. I used 80 for my denominator this time. And again, set up my proportion and I solved it, okay? So make sure you're looking at the steps for isolating your variable. Whatever you do to one side, you do to the other side to clear those out and get your variable by yourself. Okay, so make sure you fill in all your work. Make sure you have your first and last name on this. And you're going to be turning this into the drawer at the front of the room before you leave today. So let's log in again to Google Classroom and let's check out your Google form that's going to have you practice theoretical probability. And I'll see you guys on Tuesday. Thank you.